Welcome back to the next and last video of chapter 9, everybody. Today we're going to finish the construction of the universal deformation ring. Okay, so recall the main theorem we're trying to prove. Theorem 1, if V is an absolutely irreducible representation, let's say, of some profinite group, then there is a ring R in C. C here, remember, is the category of complete local Noetherian O algebras with residue field little k for some fixed ring O. And there's also a deformation D in DBR, which is the deformations from V to R, deformation classes from V to R, that is, such that for all rings A in this category C, there's a bijection from C maps from R to A with deformations from V to A. Okay. 2, the pair RD is determined up to unique C isomorphism by the first property. So we've already proven these over the last several videos. 3, R is Noetherian if and only if its K dimension of H1G NKV is finite. And we have not proven this yet. And 4, if R is Noetherian, then R is M-adically complete, where M is the maximal ideal of R. And for each A and C, there's a well-defined bijection, of course, from O algebra maps from R to A with deformations from V to A. Okay, so we have to prove these. We've also done some reductions, though. So what's left to do is we've reduced the proof of this to its part 3, so to this guy here. And then we've reduced part 4 to the following proposition several videos ago, which we called proposition 1. And it says, let A and C be Noetherian, then the topology on A equals the M-adic topology, and A is M-adically complete. So it's like complete implies M-adically complete, I guess, in this setup. Furthermore, every O algebra homomorphism A to A prime with A prime and C is actually continuous. Okay, so we got to prove this, and we have to prove theorem 1, part 3, and then we're done. So we're gonna take care of proposition 1 first. First, we need a lemma from algebra. Suppose we have a sequence of projective systems, M1I to M2I to M3I. And suppose we know for each I that this is an exact sequence of finitely generated A sub I modules for some, rings A sub I. Assume also that for each I prime less than or equal to I and J equals 1, 2, or 3, that the transition map MJI to MJI prime is AI linear. Then there's an induced sequence on the inverse limits over I of M1I, M2I, and M3I respectively. And this turns out to be an exact sequence of A modules. Okay. I suppose I didn't define my terms here. I should have done that. I think I have this. This should have been before the lemma. What we're dealing with here is a ring A and C. And we've written A as the inverse limit over I of A sub I, where the limit is over a collection of discrete Artinian quotients of A. If you watched all my chapter 8 videos, this is a very common technique in this theory, the theory of deformations. Okay, and then M and M sub I are the maximal ideals of A and A sub I respectively. Okay, so that should have been before the lemma. All right. So all of that lemma plus all of the information above now tells us that the following proposition now finishes the proof of proposition 1, and we'll call this proposition 4. So proposition 4, the following are equivalent. A in the setup above is Noetherian, and B, the K dimension of M sub I mod M sub I squared is a bounded function of I. And then if these conditions hold, the following also hold. M to the A is the inverse limit over I of M sub I to the A for all A non-negative. And the topology on A is the M-adic topology. Okay, so hopefully you can see with not too much convincing yourself that this is enough to prove proposition 1. Okay, let me say a little bit about that. If you want the last statement of proposition 1, for example, what you do is you write A prime as the inverse limit over I of A prime sub I, where A prime sub I are Artinian. And we note that for each I, the map from A to A prime sub I is continuous in the M-adic topology on A by what we're given. Okay, and then the first part of proposition 1 literally directly follows from proposition 4. Okay, in fact, we've already used this same kind of argument. If you remember, back when we tried to prove proposition 2 of this chapter, in the case that our group G we were representing is finite. So this should be a kind of familiar argument to you. Okay, let's look at the proof. I'm just gonna throw breadcrumbs at you because I think you can do most of this yourself with algebra and maybe a couple days. Okay, if you want details, you can see the Cornell Silverman Stevens text, page 321. That the first one implies the first two. So this to this is literally immediate if you know your algebra. Okay, that the first two implies the second one follows from induction on A and 2 applications of the lemma above I just gave you on inverse limits. Okay, so that the first one implies the second one. Or I'm sorry, that the first two implies the second one. You use induction on A, and you use this lemma up here on inverse limits twice, actually. See if you can do it, okay? And then the first two and the second one plus the lemma on inverse limits imply the second two. So you take these two plus the lemma I gave you, and you get this, okay? And then finally, that the first one follows from the second one and two, and then Hilbert's basis theorem, actually. Okay, so we still need this, but you kind of use all these in Hilbert's basis theorem to get that, and then you're done. Okay, so that's proposition 4. So now let's finish theorem 1. It suffices now, it remains actually to prove theorem 1 part 3. Okay, which let's go back up and review what that says. That says that my universal deformation ring is Noetherian if and only if the k dimension of its first cohomology group, H1G NKV, is finite. Okay, so let's prove that. So let's consider deformations of V to the ring A equals K bracket epsilon with epsilon squared equals 0, so the ring of dual numbers. We'll write R, our universal deformation ring, as a projective limit of its discrete Artinian quotients R sub I, big surprise, and we'll let M sub I be the maximal ideal of R sub I. The following is all either easy to check or known. You know that C maps from R to K bracket epsilon. Those are the same as a set as the limit over I of O algebra maps from R sub I to K bracket epsilon. And then that limit is the same thing as the limit over I of K maps from M sub I mod M sub I squared plus M sub O R sub I to K. This is just basically just algebra. And then this second equality here is explained in chapter 8 in the deformation theory chapter that I've already gone through. Okay, this is one of the main results there, or at least it follows from one of the main results there. Okay, so we're going to call this rightmost set here T. This is a K vector space. Okay, now O is Noetherian. So that means the K dimension, which we'll call D, of M sub O mod M sub O squared is finite. And then it's a really easy check that the K dimension of M sub I mod M sub I squared plus M sub O R sub I, so kind of this guy here, and the K dimension of M sub I mod M sub I squared, so the same thing kind of without this piece here, those differ by at most D. This is a little algebra exercise, all right? Now, the transition map of my colimits associated injective system, you can check those transition maps are injective, okay? And so this plus that injectivity come together and tell you that the K dimension of T is finite if and only if the K dimension of M sub I mod M sub I squared is bounded. But then by the previous proposition that we just finished proving, that is equivalent to R being Noetherian, okay? So I want R Noetherian, and so now I just have to check dim KT finite by this slide, all right? So let's do that. By 1 of theorem 1, the deformations from V to K bracket epsilon can be identified with T. And so if we choose a K basis for V, there's a surjection from rho bar maps from G to GLN of K bracket epsilon to T, all right? But then I also know that GLN of K bracket epsilon is just GLN of K direct sum MNK epsilon. And the homomorphisms on the left-hand side of this map here, so these guys, are easily checked to be exactly the maps that look like G maps to 1 plus C of G epsilon times rho bar of G, for which C from G to MNK is a continuous 1 cocycle. And then it's a quick check that 2 1 cocycles will give the same deformation to K bracket epsilon, so the same image in T, if and only if they differ by a co-boundary. In other words, there's a bijection from H1 of GNKV to T, okay? All right, well, great. If K is finite, I'm just done then. I mean, this is definitely going to have, finite K dimension. But if not, you can just check that this bijection is not just a set theoretic bijection, it's actually K linear, and then you're still done anyway. Okay, so that's kind of the neat little trick at the end there. And there you go, guys. So that was a little sketch there. We're done with the proof of the construction of the universal deformation ring. I am going to go on next video to Weil's algebraic criteria for complete intersections. So I will start that next video. Thanks for watching, and I'll see you all then.